Welcome! In this session, we'll explore LeetCode problem number 1840, maximum building height. This problem challenges us to determine the maximum height a building can reach while adhering to specific constraints. We'll walk through the problem, analyze the constraints, and discuss the optimal solution. Let's dive in. In this problem, you are tasked with finding the maximum possible height of the tallest building in a sequence. The problem involves two integers, n and m, where n represents the total number of buildings, and m represents the number of restrictions provided. These restrictions are given in the form of an array, where each restriction is a pair, r_i, max height _a. This means that the building at position r_i must have a height that is less than or equal to max height _i. It's important to note that the restrictions array may be empty, meaning there are no constraints other than the natural structure of the problem. The first building, building 1, always has a fixed height of 0, and your goal is to determine the maximum height that can be achieved by any building in the sequence while adhering to the given restrictions. The output of the problem is a single integer, which represents the maximum possible height of the tallest building. To illustrate this, let's look at an example. If n equals 5, m equals 2, and the restrictions are 2, 1, 4, 1, the output would be 2. Here's why: the first building has a height of 0. The second building, due to the restriction, can only have a maximum height of 1. As you move to the third building, it can reach a height of 2, which is the tallest possible height in this scenario. The fourth building is restricted to a height of 1, and the fifth building, which has no restriction, can transition smoothly to a height of 2. Therefore, the tallest building height in this case is 2. Now, consider a scenario where there are no restrictions. For instance, if n equals 6, m equals 0, and the restrictions array is empty, the output would be 5. With no restrictions, the heights of the buildings can increase steadily from building 1, which has a height of 0, to building 6, which reaches a height of 5. In this case, the absence of restrictions allows for a maximum height that simply follows the natural rule where the height difference between consecutive buildings is at most 1. This example highlights how the lack of constraints enables a smooth and consistent increase in height across the sequence of buildings. Let's examine another example with restrictions. If n equals 10, m equals 2, and the restrictions are 3, 3, 6, 2, the output would be 5. Here's the reasoning: building 1 starts with a height of 0. By the time we reach building 3, its height is capped at 3 due to the restriction. Moving onward, building 6 is restricted to a maximum height of 2. However, the tallest possible building height in this configuration is achieved at building 5, which can reach a height of 5 while still adhering to the given constraints. This example demonstrates how the problem balances maximizing height while respecting all restrictions. Finally, let's consider the constraints and additional notes. The constraints specify that the total number of buildings, n, can be as large as 10 to the power of 9, and the number of restrictions, say m, is limited to the smaller value between 10 to the power of 5 and n. Each restriction is unique, meaning no two restrictions apply to the same building. Additionally, the heights of buildings must either increase or decrease by at most 1 between consecutive buildings if no restrictions are present. When restrictions are provided, the solution must ensure that all height limits are respected while still maximizing the tallest building's height. This emphasizes the importance of processing the input efficiently to handle large values of n and m within the constraints of the problem. To solve the maximum building height problem, our goal is to determine the tallest possible height a building can reach while adhering to the given height restrictions. These restrictions apply to specific buildings, and the challenge lies in distributing heights between these restricted points in a way that maximizes the tallest building. A naive approach we can consider is the brute force method. Here, we iterate through all possible heights for each building, ensuring that the constraints between restricted buildings are met. For example, we compute the maximum height for every building located between two restricted buildings, propagating these constraints forward and backward to maintain consistency. However, while this approach is straightforward, it becomes highly inefficient as the number of buildings increases. The time complexity of O(n squared) arises because we repeatedly check all pairs of buildings and enforce constraints iteratively. For scenarios where the total number of buildings, n, is very large, potentially up to 10 to the power of 9, this approach becomes impractical due to its computational demands. Now, to overcome the inefficiencies of the brute force method, we can turn to an optimized approach that combines greedy techniques with binary search. This strategy focuses on the restricted buildings and their neighbors, allowing us to propagate constraints in both directions more efficiently. The process begins by adding implicit restrictions for the first and last buildings. For instance, the first building is restricted to height 0, and the last building has a maximum possible height of n1. Next, we sort the restrictions array based on the building indices. Following this, we perform a forward pass from left to right, enforcing the slope constraints between consecutive buildings so that the height difference is valid. Then, we do a backward pass from right to left to ensure that all constraints are properly satisfied in both directions. Finally, we calculate the maximum possible height between restricted buildings using a triangular height increase formula, which ensures that the tallest building is positioned at the midpoint. This approach significantly improves efficiency, as sorting the restrictions takes m log m, and the forward and backward passes take linear time, resulting in an overall complexity of m log m. This makes it suitable for large N, as the focus remains on the smaller set of restricted buildings. The optimized approach is the clear choice for this problem because it is both efficient and scalable. The key insight is that the heights between restricted buildings naturally form a triangular structure, with the maximum height occurring at the midpoint. By sorting the restrictions and enforcing constraints in both directions, we ensure that all requirements are met while maximizing the building heights. Additionally, the constraints of the problem, such as the potentially large value of n and the relatively small number of restricted buildings m, make this strategy particularly effective. Instead of iterating over all buildings, we focus only on the restricted ones, which significantly reduces computational overhead. When comparing the two methods, the brute force approach, while simpler, is impractical for large inputs due to its n² complexity. In contrast, the optimized approach, though slightly more complex to implement, achieves a balance between correctness and performance with its m log m complexity. By leveraging the triangular height formula and propagating constraints bidirectionally, this solution avoids unnecessary computations, making it both intuitive and efficient for solving the problem at scale. In this problem, we are tasked with determining the maximum height a building can achieve under a set of constraints. Specifically, we have n buildings numbered from 1 to n, and the heights of adjacent buildings can differ by at most 1. Additionally, some buildings have predefined height restrictions, given as index max height, meaning a building at a specific index cannot exceed a specified height. To solve this problem efficiently, we use a two-pass greedy algorithm. The first step in this process is to pre-process the restrictions by adding two artificial constraints. These are a restriction at index 1 with a height of 0, and another at index n with a height of n1, which is the maximum height allowed at the last building. These artificial constraints help simplify boundary conditions and make the algorithm more robust. After adding the artificial constraints, we combine them with the input restrictions and sort the list by building indices. This ensures that we process restrictions in order of their positions, laying the groundwork for the next steps. Now, the algorithm proceeds with a left-to-right pass through the sorted restrictions. During this pass, we ensure that the height at each restricted index does not violate the adjacency rule of a height difference of at most 1. For a restriction at index_i with a current height_i, we adjust its height based on the previous restriction at index_prev with height_prev. Specifically, the height at index_i is updated to the minimum of its current value and height_prev plus the distance between the two indices. This adjustment guarantees that the height at index_i respects both the restriction and the adjacency constraint. Following the left-to-right pass, we perform a right-to-left pass through the same sorted restrictions. The logic here mirrors the previous step but propagates constraints in the opposite direction. For a restriction at index_i with height_i, we adjust its height based on the next restriction at index_next with height_next. The height at index_i is updated to the minimum of its current value and height_next plus the distance between the indices. This ensures that the height at index_i respects the adjacency rule when moving from right to left. After these two passes, the restrictions array contains the maximum possible heights at all restricted indices, consistent with the problem's constraints. The next step is to compute the maximum achievable building height between the restricted indices. To calculate the maximum height, we iterate through the restrictions and focus on the intervals between consecutive restricted indices. For two restrictions at index 1 with height 1 and index 2 with height 2, the maximum height achievable between these indices occurs at or near the midpoint. The formula to compute this is height 1 plus height 2 plus index 2 index 1 // 2. This accounts for both the adjacency constraints and the heights at the endpoints. By applying this formula across all intervals, we track the overall maximum height. The greedy propagation in the left to right and right to left passes ensures that restrictive heights are minimized, while the midpoint calculation helps identify the global maximum. The artificial constraints at indices 1 and n further simplify boundary conditions, ensuring a streamlined approach to solving the problem. The core data structure here is the restrictions array, which we sort and update efficiently during the algorithm. With a time complexity of O, k * log, k, and constant space usage, this approach is both efficient and scalable. It's important to handle edge cases carefully to ensure the algorithm is robust. If there are no restrictions provided, the solution reduces to the maximum height of n1, as all buildings can grow without limitations. For a single restriction, the artificial constraints naturally handle the scenario. In cases where the restrictions impose severe height limitations, the algorithm adjusts heights accordingly without violating constraints. Let's consider an example to see this process in action. Suppose n equals 5 and restrictions equals 2, 1, 4, 1. First, we preprocess the restrictions by adding 1, 0, and 5, 4, resulting in 1, 0, 2, 1, 4, 1, 5, 4. During the left to right pass, the heights are adjusted to 1, 0, 2, 1, 4, 1, 5, 2, to ensure the adjacency rule is respected. Now, in the right to left pass, we adjust the heights again to account for constraints in the opposite direction. Starting from 5, 2, the heights are updated to 4, 1, 2, 1, 1, 0. Finally, we compute the maximum building height. By examining the intervals between restrictions, we find that the maximum height of 2 is achieved between buildings 2 and 4. This demonstrates how the algorithm efficiently handles restrictions and adjacency constraints to determine the optimal solution. The combination of preprocessing, greedy passes, and midpoint calculations makes this approach both effective and intuitive, ensuring it works seamlessly across a variety of scenarios. Here, we start by defining a function called maxBuilding within the solution class. This function takes two parameters, n, which represents the number of buildings, and restrictions, a list of constraints on the heights of specific buildings. The first step is to ensure that we include restrictions for the first and last buildings. For the first building, its height is fixed at 0, and for the last building, its height cannot exceed n1. These are appended to the restrictions list. Next, we sort the restrictions based on the building index to ensure the constraints are processed in the correct order. Now, we perform a forward pass through the restrictions list. The purpose of this step is to enforce valid height constraints as we progress through the list. For each restriction, we calculate the maximum allowable height by considering the current restrictions index, the previous restriction's height, and the distance between them. This ensures that no building exceeds the permissible height based on the constraints given so far. Following this, we perform a backward pass to refine these constraints. This step ensures that the heights remain consistent when traversing the restrictions in the reverse direction. By iterating backward, we adjust the heights where necessary, considering the next restriction's height, index, and the distance between consecutive restrictions. This two-pass process guarantees that the height restrictions are valid and consistent in both directions. Finally, we calculate the maximum possible height that any building can achieve while satisfying all the given restrictions. To do this, we iterate through the restrictions list once more. For each pair of consecutive restrictions, we calculate the maximum height that can be achieved between their indices. The key observation here is that the tallest point between two restrictions occurs at the midpoint of their indices, where the height transitions smoothly. Using the formula for the midpoint height, which considers the heights of the two restrictions and the distance between them, we update the maximum height encountered so far. After completing this calculation, the function returns max_height, which represents the tallest possible building height under the given constraints. Here, we start by importing the necessary libraries and defining our Java solution. The function maxBuilding takes two inputs, the total number of buildings n and an array of restrictions, where each restriction specifies a building index and its maximum allowable height. To simplify the problem, we add two additional restrictions. The first ensures that the height of the first building is 0, and the second ensures that the height of the last building is within the maximum allowable range. These are added to a list called restrictions list. Next, the list is sorted by the building index to make it easier to process in order. After sorting, we perform a forward pass through the list. This pass adjusts the maximum heights, ensuring that each building's height respects the restriction of the previous building and the distance between them. For example, if the previous building is at a certain height, the current building's maximum height must be limited by both its restriction and the distance from the previous building, which is calculated as the difference in their indices. This ensures that no building height increases too sharply. After the forward pass, we perform a backward pass through the restrictions list. This pass ensures that the maximum heights are further adjusted, taking into account the restrictions of the subsequent buildings and their distances. Once both passes are complete, we calculate the maximum possible building height. This is done by iterating through each pair of consecutive restrictions in the list. For each pair, we determine the maximum height that can be achieved between the two buildings. This is calculated as the average of their adjusted heights, plus the distance between them, divided by 2. By taking the maximum value across all pairs, we determine the maximum possible building height for this configuration. Finally, the function returns this value as the result. In this example, we start with a small input where there are no additional restrictions beyond the boundaries of the buildings. The input specifies n equals 5 and an empty restrictions array. The first step is to add boundary restrictions. These represent the minimum and maximum possible heights at the edges of the range, so we add 1, 0 for building 1 with height 0, and 5, 4 for building 5 with height 4. After adding these, the restrictions list becomes 1, 0, 5, 4. Since the restrictions list is already sorted by building index, no sorting is necessary. Next, we perform a forward pass to ensure the constraints are valid as we move left to right. In this case, we compare 1, 0, and 5, 4. The maximum height at building 5, calculated as 0 plus 5 to 1 equals 4, is already valid, so no changes are made during the forward pass. At this point, the restrictions remain 1, 0, 5, 4. Now, we perform a backward pass to ensure the constraints are valid moving right to left. Comparing 5, 4, and 1, 0, we find that the maximum height at building 1, calculated as 4, 5 to 1 equals 0, is already valid. This means no changes are made during the backward pass, and the restrictions remain 1, 0, 5, 4. Finally, we calculate the maximum possible height. The highest point between 1, 0, and 5, 4 occurs at the midpoint. The distance between buildings 1 and 5 is 5, 1 equals 4. Using the formula, height 1 plus height 2 plus distance, ///2, the maximum height is 0 plus 4 plus 4, //2 equals 4. Therefore, the final output for this example is 4. In this second example, we introduce restrictions within the range of buildings. The input specifies n equals 6 and restrictions equals 3, 1, 5, 2. First, we add the boundary restrictions 1, 0 for building 1 and 6, 5 for building 6. After this step, the restrictions list becomes 3, 1, 5, 2, 1, 0, 6, 5. Next, we sort the restrictions list by building index to ensure proper processing order. After sorting, the restrictions become 1, 0, 3, 1, 5, 2, 6, 5. This sorted list allows us to validate the constraints in both forward and backward passes. The forward pass begins by comparing adjacent entries to ensure the constraints are valid moving left to right. First, we compare 1, 0, and 3, 1. The maximum height at building 3, calculated as 0 plus 3 to 1 equals 2, is greater than the current restriction height of 1, so no changes are made. Next, comparing 3, 1, and 5, 2, we find the maximum height at building 5 is 1 plus 5 to 3 equals 3, which is greater than or equal to the current restriction height of 2, so no updates are needed. Finally, comparing 5, 2, and 6, 5, the maximum height at building 6 is 2 plus 6 to 5 equals 3, which is less than the current restriction height of 5, so we update 6, 5 to 6, 3. After the forward pass, the restrictions become 1, 0, 3, 1, 5, 2, 6, 3. In the backward pass, we validate constraints moving right to left. Comparing 6, 3, and 5, 2, we find the maximum height at building 5 is 3, 6 to 5 equals 2, which matches the current restriction. Similarly, the maximum height at building 3, calculated as 2, 5 to 3 equals 1, remains valid, as does the maximum height at building 1, calculated as 1, 3 to 1 equals 0. No changes are needed during the backward pass, so the restrictions remain 1, 0, 3, 1, 5, 2, 6, 3. Finally, we calculate the maximum height. Between 1, 0, and 3, 1, the maximum height is 0 plus 1 plus 2, / 2 equals 1. Between 3, 1, and 5, 2, the maximum height is 1 plus 2 plus 2, / 2 equals 2. Between 5, 2, and 6, 3, the maximum height is 2 plus 3 plus 1, / 2 equals 3. The final output for this example is 3. In the third example, we consider a larger input where n equals 10 and there are no restrictions other than the boundaries. First, we add the boundary restrictions 1, 0 for building 1 and 10, 9 for building 10. This gives us the restrictions list 1, 0, 10, 9. Since the list is already sorted, no further sorting is necessary. During the forward pass, we compare 1, 0, and 10, 9. The maximum height at building 10, calculated as 0 plus 10 to 1 equals 9, is already valid, so no changes are needed. The restrictions remain 1, 0, 10, 9 after the forward pass. In the backward pass, comparing 10, 9, and 1, 0, the maximum height at building 1 is calculated as 9, 10 to 1 equals 0, which is valid. As a result, no changes are needed, and the restrictions remain 1, 0, 10, 9. Finally, we calculate the maximum height. The highest point between 1, 0, and 10, 9 occurs at the midpoint. The distance between buildings 1 and 10 is 10, 1 equals 9. Using the formula, height 1 plus height 2 plus distance, / 2, the maximum height is 0 plus 9 plus 9, / 2 equals 9. The final output for this example is 9. Now, let's break down the time complexity of the algorithm by analyzing its main components. First, consider the sorting step. We apply the sort function to the restrictions list, which includes the original m restrictions plus 2 additional boundary restrictions. Since sorting a list of size m plus 2 takes O, m plus 2, * log, m plus 2, and for large values of m, the constant 2 becomes negligible, this simplifies to O, m * log m. Next, we perform a forward pass through the restrictions. Here, we iterate once over the list, adjusting the maximum allowed height for each restriction based on the previous one, which takes linear time, or O, m. Finally, there's the backward pass, which is similar in structure to the forward pass but ensures constraints are valid when moving in reverse. This also involves a single iteration over the list, taking another O, m time. Each of these steps contributes to the overall time complexity, with sorting being the most computationally expensive step so far. Now, for the final step, we calculate the maximum possible building height after processing the restrictions. This involves iterating through the adjusted restrictions list to compute the height for each segment. This step, like the forward and backward passes, is a linear operation, requiring O, m time. When we combine all these steps, the total time complexity is determined by the sorting step, which dominates due to its O, m * log, m complexity. Adding the linear contributions from the forward, backward, and final height calculation steps results in O, m * log, m, plus O, m, plus O, m, plus O, m. Simplifying, the overall time complexity remains O, m * log, m. Importantly, while the total number of buildings n does not directly affect the runtime, the number of restrictions m governs the complexity because the algorithm processes the restrictions list rather than iterating through all buildings. Turning to the space complexity, the algorithm is highly efficient in its use of memory. The input restrictions list is modified in place, so no extra space is required for storing a copy of the list. Additionally, the algorithm uses only a constant amount of auxiliary space, such as variables for loop indices and temporary calculations during the forward and backward passes. Even during the sorting step, the sort operation is performed in place, meaning no additional memory is allocated for sorting. As a result, the total space complexity of the algorithm is 1, as it does not rely on any extra data structures or significant memory allocations beyond the input and a few constant variables. Finally, let's compare this optimal solution to a brute force approach. A naive method would involve iterating through all possible building heights for every building from 1 to n and verifying whether the restrictions are satisfied for each configuration. This would result in a time complexity of n squared, or worse, depending on the exact implementation, making it impractical for large values of n. In contrast, the current solution leverages the given restrictions to simplify the problem. By reducing the focus to the much smaller restrictions list, the time complexity is drastically reduced to m log m, where m is typically far smaller than n. This efficiency is due to sorting dominating the runtime, as it grows faster than the linear passes for large m. Moreover, the space complexity remains 1, ensuring minimal memory usage. In summary, this approach is highly optimized for scenarios where n is large, and m is relatively small, which is common in real-world applications. When tackling this problem, there are a few common mistakes to watch out for. First, many people misinterpret the constraint that the height difference between adjacent buildings cannot exceed 1. It's crucial to enforce this rule carefully during both the forward and backward passes of your solution. Next, edge cases can be tricky. For example, if the restrictions array is empty, you need to handle the scenario where there are no specific constraints. Similarly, when restrictions cover all buildings, your implementation must still function correctly under these conditions. Another issue arises with sorting. The restrictions array must be sorted before you perform a linear traversal, as an unsorted array can lead to incorrect height calculations. Another frequent error is in height propagation. Failing to propagate constraints consistently in both directions, left to right and right to left, can result in mismatched heights and incorrect results. Finally, some solutions are unnecessarily complex, involving nested loops or redundant calculations, which can lead to time-limit-exceeded errors. Remember, a simple two-pass approach with sorting is both efficient and sufficient for this problem. Now, let's talk about how this problem is often approached in interviews. A key pattern to recognize here is the concept of propagating constraints forward and backward. This propagation technique is commonly used in other problems that involve calculating maximum or minimum feasible values under certain rules. The optimal strategy involves sorting the restrictions array and then processing constraints in both directions. Highlighting this approach during an interview shows that you understand the structure of the problem and its efficient solution. Additionally, interviewers often test your ability to handle edge cases, such as scenarios with only one building, no restrictions, or very large input sizes. It's important to practice reasoning through such cases to build confidence. If you have time during an interview, discussing trade-offs between different approaches can also be valuable. For instance, you can explain why brute force is less efficient compared to the two-pass propagation method. This demonstrates not only your problem-solving skills but also your ability to evaluate the efficiency of alternative solutions. There are several related problems on LeetCode that share conceptual similarities with this one. For example, LeetCode 410, split array largest sum, involves dividing an array while minimizing the maximum sum, which requires working within constraints. Similarly, LeetCode 1011, capacity to ship packages within D-days, and LeetCode 875, cocoa eating bananas, both involve constraint-based calculations to determine optimal values. Even LeetCode 130, surrounded regions, while different in context, also requires propagating constraints across a grid, making it conceptually related. When considering alternative approaches, brute force is one option, but it's quite inefficient. Iterating over all buildings and calculating maximum heights for each one results in a time complexity of n*m, where n is the number of buildings and m is the number of restrictions. A better approach is the two-pass propagation method, where you first sort the restrictions and then process constraints in forward and backward sweeps. This reduces the complexity to O, n plus m asterisk log m, making it optimal. Dynamic programming is another option, but it can unnecessarily complicate the solution unless additional constraints make it essential. The optimal solution to this problem has a time complexity of O, n plus m asterisk log m, where n represents the total number of buildings and m represents the number of restrictions. This efficiency is achieved by sorting the restrictions and then performing two linear passes to propagate constraints in both directions. The sorting step accounts for the log m factor, while the linear traversal ensures the solution scales well with the input size. This balance between simplicity and efficiency makes the two-pass propagation method the preferred approach. Great job! We've completed our discussion of LeetCode number 1840, maximum building height. We summarized the problem, explored an efficient algorithm, and highlighted key takeaways. Thanks for watching. Be sure to like, share, and subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!